It's my great pleasure to introduce Marcelo Bertalmío.
Excellent. Thank you.
Who is going to talk to us about visual phenomena. From my cursory understanding, Marcelo received his undergrad degrees in electrical and electronic engineering. That's what I did from and his PhD in Minnesota, also in electrical and electronic engineering. He worked in Spain as a full professor. It looks like he had a very diverse career, including co-founding startups. And I will let you tell us more. But thank you for coming to the conference, and very much look forward to it.
Thank you, Dan. It's really great fun being here. So let me just jump directly into the talk. So this is now where I should ask, how do I go to the next slide? It's not this button, right?
The mouse and we'll set it.
Excellent. And if I want to go back, oh, yes, it works. Thank you very much. So the so-called standard model of vision. This is work from the mid-20th century. The receptive field of a neuron is defined, or was defined originally as the action, the range in the visual field where a light activity influenced the response of a neuron. And the work of Koffler in 1953 showed that you could model pretty well the response of a neuron by making a filtering of the input light stimulus with some weights, and the filter, it was the so-called receptive field of the neuron. And Hubel and Wiesel took this further and showed that this was also happening in the cortex, where the receptive field now had an oriented shape that again allowed to represent the response as a filtering operation on the input stimulus to the neuron. Then Rodek showed that the predictive power of this simple model could be improved if at the end, after the filtering, you introduced a nonlinearity. So that's what's known as the standard model of vision, a linear plus nonlinear formulation that is used in cascades. So you do a linear filtering, then you have nonlinearity, which I call here sigma, and you do this in cascade, and you are able to replicate neural phenomena. In this case, I'm showing for schematic neurons from the retina to the cortex, and also simple and complex neurons. And this idea of the standard model was incorporated into visual perception modeling through the work of Campbell and Robson, which showed that it's possible to model perceptual phenomena like the perception of brightness, motion, contrast, by representing the activity of the visual system as a number of channels that are that are tuned to orientations and spatial frequency, and also subject to nonlinear operations. And most models in visual perception have this form of a bank of filters and with interspersed nonlinearities. And this is also the inspiration behind artificial neural networks, in which the neuron model also follows that approach of linear filtering and nonlinearity, and there's a hierarchy of levels. So this linear nonlinear paradigm remains as the foundation of most models of visual neuroscience and visual perception, and it's the cornerstone of artificial neural networks. There are a number of problems inherent to considering that the receptive field has a linear form. For instance, visual adaptation makes the linear receptive field change with the input. Also, your measurement of the linear receptive field depends on the choice of basis functions you use to measure it. And finally, the linear RF is not supported by more recent neuroscience that shows that actually the summation is not really linear. And just a short inroad into dendritic integration. So it's been shown, but it's much more recent work than, mainly this is the greatest advances have been on this specific area have happened in the past maybe 3 decades. Dendrites do not only perform passive integration, so the usual summation. They also do active integration, where the summation is passed through a nonlinearity. And also something that happens is that this nonlinearity is affected by signals coming from the soma, the so-called backpropagation action potentials, and that this affects the nonlinear properties of the dendrites. Also,
is that brain data or simulation?
this is real data. Yes. Yeah. Also, these properties of dendrites depend on where they are in the neuron, and also depend on to which neuron they belong. So you can have supralinear or sublinear nonlinearities, and also fairly recently it's been shown that they can have a specific nonlinearity that corresponds to the XOR operation, something that in the standard model requires 3 full neurons. It can be performed just with a single dendrite. Accurate modeling of dendrites it's essential for computational neuroscience to get accurate models for a number of tasks. And also this does influence perception. So both at cortical levels, at a cortical level, and also at retinal level, accurate motion detection at the retina requires dendritic nonlinearities that change with the input, both for vertebrates and insects. These are fairly recent results. So a limitation current, sorry. I have my stopwatch here, so I can, a limitation that is common to current models in vision neuroscience and artificial neural networks is the following. You get poor performance or failure unless these models can change with the input. But it is not known how to make this model self-adaptive to the input. And this is a key thing. So for instance, in visual perception, there are a number of phenomena that have been observed, some of them for many years, that you cannot predict. These are psychophysical experiments, right? The results you cannot predict with a standard model or with the standard model unless you manually tune the parameters when the input changes. So this happens for the for white illusion and under bandpass noise, for this brightness perception phenomena called the crispening effect observed by Whittle. So the brightness response curve is not logarithmic, it's not a power law, it has this weird shape, but it also depends on the sort of image, the color and the background. This is a very shocking example from the already from the 70s. This phenomena where you have signals that have very different orientation, but nonetheless, they mask each other, which totally contradicts the standard model. And this has the state-of-the-art model in visual perception for this is not able, the state-of-the-art model of visual contrast perception is not able to replicate this data. So if you want accurate results, you don't use models, you use people. So if your standards of quality are really high in modeling, the appearance of images are really high, you, like in cinema, you have colorists, you have people with very good eyes that are able to do what visual models cannot. And in deep learning, I am sorry, I won't have time. This is a fascinating topic, of course, and I won't have time in this presentation to go in depth, but I wanted to mention these key points, which are maybe not so well known in the field, which is one of the main limitations of deep learning can be seen as failures to emulate human vision phenomena. For instance, deep learning methods to classify images have a good performance or an excellent performance in a test set, but if you change, you test them on different images, then the performance drops significantly. And there's this adversarial attack problem. You add a very slight perturbation to your image, and the network completely misclassifies the image, completely. Something that does not happen for humans. Also, this does not happen for humans. We are pretty robust, not completely robust, but we are pretty robust in classifying chairs, regardless of if they are on top of a cupboard or inside a car or whatever. And this is something that networks cannot do. So these two problems of networks, deep networks not being robust and accurate at the same time, actually it has been shown fairly recently through a number of papers from a math group in Cambridge that these problems are unavoidable. So there's mathematical proof that deep neural networks cannot be at the same time robust and accurate. So if they're accurate, they're unstable. So we cannot avoid adversarial attacks unless, and this is, so these are 3 papers. We cannot avoid them unless the networks are able to adapt to the input, to change their size and dimensions with the input. Okay, so there's math proof for that. Okay, and there's a couple of papers which are fantastic on how deep neural networks are not good models of vision. Okay, so AI researcher Gary Marcus, very prominent AI researcher, says that maybe the problem is that we're using dumb neurons. We should use smarter neurons. And going to, oh man, yeah. Visual neuroscience, you have in visual neuroscience phenomena, which is very puzzling, and you can, again, you cannot explain with the standard model unless you go there and change the parameters in an ad hoc way. Like cells that are off for some input, they become on for some other input. This is really puzzling, and it does happen, both at cortical and retinal level. So if you want to use neural modeling to predict neural activity given natural image stimulus, the situation is worse. So in 2005, the top predictive power was like 30% or 40% of the response variance of V1 neurons. And they were not optimistic that this could be improved, given that they said that the bread and butter of the model is the linear filtering. And 15 years later, the state of the art had improved only, not so much, from 40 or, going up to 50% the most. This is the 3rd time we quote Olshausen today. I love this quote, so I will read it. The problem is not just that we lack the proper data, that we don't even have the right conceptual framework for thinking about what is happening. My own view is that the standard model is not just in need of revision. It is the wrong starting point and needs to be discarded altogether. What is needed in its place is a model that embraces the true biophysical complexity and structure of cortical microcircuits, especially dendritic nonlinearities. So after this long-winded introduction, we propose this model, the intrinsically nonlinear receptive field, where the motivation was the following. So we wanted something, an alternative to the linear receptive field that is more biophysically plausible. So we considered these 3 aspects that were ignored or are ignored by linear filtering. 1, so dendrites can be nonlinear. 2, this nonlinearity may be different from one dendrite to another. And 3, there's feedback from the neuron soma to the dendrites. So by fusing all these aspects, we propose the INRF model where the output at location X is composed of the sum of 2 terms. The first term is just a regular linear filtering operation. So M will be like a linear filter. And that corresponds to passive dendrites. And the second term corresponds to active dendrites, where the nonlinearity is sigma. That's the nonlinearity of each dendrite. And it is affected by a signal that comes from the soma, which is that feedback minus G convolved with IX. Okay. So
X, what is it?
So sorry, might be an unusual notation. So X is the location of the neuron where we are modeling the response with INRF. And the Y's are the locations of the neighbors. And I is the signal. Okay.
What's INRF stand for?
Intrinsically Nonlinear Receptive Field. Yeah, this is obscured by my image.
Sorry, so Y sub I is
So y sub I is the location of a neighboring neuron.
Okay, even if I is the ith neighboring neuron.
Yes, yeah. Yeah.
Wait, location in visual space?
In a space, yes.
And the activity.
The activity is I, capital I. So y is the location. Sorry, maybe I misunderstood. So y is the location of the neighbor, and capital I is the signal at that location. Yes. Yeah. Yeah.
Then it's INRF. I guess how it's finally related to INRF.
I'm sorry. Can you repeat that question? If I may, if you keep it to the end, I can probably be able to end faster and devote. Yeah, thank you. So this is again the same where this scheme represents that some dendrites are passive with and do linear filtering with weights m. Some dendrites are active and they do nonlinear filtering with a nonlinearity sigma that is affected by a signal that comes from the soma to the dendrite. Okay, some properties that I don't have time to explain, but they are in the paper. One, the linear receptive field is a specific case of the INRF. INRF cannot be efficiently expressed with linear filters. It has a different structure from a regular cascade of linear plus and nonlinear modules. And it can, with for specific shapes of the nonlinearity and the linear M and W, it can approximate local histogram equalization, embodying the efficient representation principle. So some results of this INRF formulation for visual perception were I'm using for M and W, just regular 2D Gaussians, okay? And sigma is a regular sigmoid. And G is just a delta, so you can ignore it, okay? Convolution with a delta gives you the same. So M and W Gaussians and sigma a sigmoid. So if you do that, we are able to reproduce the, for instance, the crispening phenomena. These are brightness perception curves whose shape change a lot with the background, and the regular model cannot explain that, but ours can. Yes.
So just to be clear, you have a whole array of neurons, and they interact with each other in a recurrent way, and you settle into
No. So what we do here for visual perception, so we have this this neural summation model, and what we do here for sorry, I should have been totally explicit. You're totally right. What we do here for visual perception phenomena is we take an image, okay, and we apply this, and we obtain an output, and we compare this output image to what we are supposed to be perceiving in that case.
So we should just think of those as static inputs.
So in this case, so capital I is the, let's say it's a grayscale image, that's the gray level, and these are static images for the moment. I will show you an example for video later. Yeah. So if we do that, we are able to reproduce the phenomena of these brightness perception curves changing with the input, but keeping our model fixed. We don't do anything to the model, okay? And also, we are able to reproduce the psychophysical results of this white solution under bandpass noise. So on the left, you get the results from the psychophysical experiment, and on the right, the results with our model. We are also able to reproduce this puzzling masking results from Darrington and Henning that I mentioned before. So there's masking here when it shouldn't be according to the standard model. And in that paper, they have this data that we qualitatively reproduce pretty well. Yeah, so I'll just go fast. We can also use the same idea also for both image and video quality assessment. So in order to have a method, an algorithm that tells you, that predicts how an observer would say that these images are, how different they are. So what we do is, since we have seen the regular comparisons like mean square error, they're not really that useful because they don't correlate well with visual perception, as this shows. Oh man, 20 minutes. Okay. So what we do is we take the images, we apply INRF, and we compare the INRF, outputs of the images, and this does correlate pretty well with visual perception. And for video, we do that frame by frame, and then we do a time pooling of the results. So by doing that, we get state-of-the-art results on image and video quality assessment, where we rank among the top metrics, even though the other metrics have millions of parameters. Sorry? The one at the bottom. So we rank third in this case. Yeah. For image, and for video, we rank first, and we are able to outperform the Netflix metric, which is very fulfilling. Anyway, we can extend this to the spatial-temporal domain using different. So we introduce temporal filtering, and we use different shapes for the nonlinearity, which is now has this kind of absolute value raised to a power. And if we do that, we are able to predict motion perception phenomena that the state-of-the-art cannot, because they are so there are different types of motion phenomena: first order, second order. Some people argue that there are third order motion phenomena, and in the literature you have different motion sensors for different kinds of motion. So you have sensors for first order motion and different sensors for second order motion. And with our model, it's more parsimonious. We can reproduce both first and second order phenomena. And yes, and just as a final note, I should probably skip that. And also that we have interesting results on visual neuroscience that Elias will be talking about next. And just as a final thing, if we take an artificial, what we did is a very simple experiment. We took an artificial neural network. We replaced the linear filters with these INRF modules, and we trained this new network for classification. And what we obtained, but the rest of the architecture was kept the same, so the same number of parameters. So what we get is that the accuracy improves a lot. The amount of training data that we need reduces significantly. Like we need just 20% of the training data, and it's also much more robust to adversarial attacks. So, and we also have some theoretical results, which I don't have time. So conclusion, this seems to us like a promising alternative to the linear receptive field. And yes, thank you very much.